Hello everyone and welcome to part 2 of my tutorial on bivariate data analysis. This is for the QCAA Queensland syllabus for general maths. This is Unit 3, Topic 1 content. Now, I will warn you, this one is probably going to be a long one. But few options. Number one, shout out to McClatchy Maths and Joel Sperenza, who both have YouTube channels where they're doing these things more lesson by lesson. So if that's more what you're after, go find them. Option 2, if you hit playback speed and hit times 1.5 or times 2, I'll sound like I'm on caffeine and you'll get through this a lot faster. Option 3, check the timestamps in the description below. Maybe there's just something in particular you want to know about. You can skip to that section. But my intention here is to try and do everything in one go so that we can cover this whole topic in a very efficient way, but also look at the whole picture that we're trying to gain here. So those are your options. I did cover this first section here in part 1 as well, so if you've already heard this bit, skip over it, look at the timestamps, and go on to where we actually start the numerical data analysis. But I was fairly certain that some people would be watching this video just by itself and not part 1, so I think it's important to go over this bit again. So first of all, we're going to talk about the goal of bivariate data analysis. So the point is to analyze data from two variables. Bivariate, bi meaning two, variate referring to variables. So we're analyzing the data from two variables to identify patterns that suggest the presence of an association or relationship between them. So I'm just going to unpack those things that I have underlined there. First of all, when we're talking about two variables, one of them will be the explanatory variable and one of them will be the response variable. Now, that's the language we're using in this syllabus, but if you come from a science background, if you do biology or some other science like that, you may be more used to these terms, independent and dependent. Same thing, different words, But the explanatory variable is the variable that is used to explain or predict a difference in the response variable. And the response variable is changing in response to the explanatory variable. The explanatory variable will be your x-axis, which is nice and easy to remember because there is an x in explanatory. And response variable will be your y-axis, or your y variable. So let me give you an example of identifying explanatory and response variables because that might be easier than those definitions. So here's our example. Amy decided to bake a cake. She put a thermometer in the cake and started a timer. She noticed that the longer the cake was in the oven, the more the temperature of the cake rose. In this case, the temperature of the cake is the response variable because it is responding to the time that it spends in the oven. And of course, the amount of time spent in the oven is the explanatory variable since it is explaining the temperature of the cake. So hopefully that helps you to understand the difference between explanatory and response variable. It's going to be important as we go through this process, so make sure you stop and reread that example if you need to. All right, our other point here, which was about association/relationship. So let's talk about that for a second. There's a phrase that you might be familiar with in mathematical and science circles, which is correlation does not mean causation. A relationship or correlation shows that there is an association between two variables. There's a relationship between them, but no more. We cannot conclude anything about the source or the cause of the association. So we cannot say that what the explanatory variable is causing a change, Okay, you cannot say that there is a causal relationship between them. Okay, even if it seems very obvious, like my example up here, of course the temperature of the oven is causing a change. But when we get to more abstract situations where we're looking at data gathered about populations, etc., we cannot say that there is a causal relationship between them. Okay, one does not cause the other. There might be other factors involved, like just pure coincidence, or there might be some other variables that are involved that are confounding the situation, that are making things confusing. Okay, now we need to categorize our data, okay, because our data can be either categorical or numerical. Okay, categorical data is data that is in categories. So my example here is a student's method of transport to school: bike, car, walk, bus, etc. Those are categories. Whereas the other type is numerical, where the data is numbers. For example, if you're measuring the height of students in year 12, you might get 165.8 centimeters or 172.35 centimeters, etc. Okay, those are numbers. So the data you are gathering is numbers in that case. So it's important that we do this because the type of analysis we choose will depend on what type of data it is. Okay, so go to part 1 of this series. I'll put it in the info card if you want to see what you need to do with categorical data. But for this video, we're going to talk about what to do if it's numerical data. Okay. When it is numerical data, you need to do something that is called linear regression analysis. Okay, so this is used to analyze bivariate numerical data. Bivariate, once again, meaning two variable data that is numbers. Okay, you will also see there's a key word here, linear. That means that the relationship is a straight line. Okay, it is out of the scope of this syllabus to really analyze non-linear relationships. Okay, we don't really go into that at all, other than to know the difference between linear and non-linear. Okay, we'll talk about that as we go through, but just bear that in mind. Okay, there's 7 steps essentially to linear regression analysis, and we're going to go through this whole process now. Okay, so first step is to construct a scatterplot. We're going to interpret the scatterplot. Then we're going to start calculating some statistics, including the correlation coefficient. We're going to fit a least squares line. We're going to use that line to make predictions. Check the validity of our model with another statistical measurement called the correlation of determination. And then check if the linear assumption is correct or not with a residual plot. Okay, so those are our 7 steps. Let's go through them one by one. Okay, so our first step is to construct a scatter plot. Okay, what better way to do that than with an example? Okay, so here I have some data that I have collected about the hours of study that students did in the week before their general maths exam, and then their result, their percentage result on the test. So you can see this first student here studied for 5 hours in the week before the test, and they got a result of 62%. Okay, so that's our example that we're going to be using throughout this whole process. Okay, so let's start by constructing a scatter plot. So you're going to have axes, of course, x-axes and y-axes. So the first thing we need to figure out is which variable goes on which axes. Okay, so this is your x-axis, and this is where the explanatory variable goes. This is your y-axis, and this is where the response variable goes. So I want you to have a look at our example, and I want you to tell me, or pause the video, write it down, which of those variables do you think is explanatory and which variable is response. Pause the video, write down an answer, and then unpause it, and I will reveal the answer to you. Okay, so our explanatory variable is the hours of study. It makes more sense that the amount of study that you're doing would impact your result rather than the other way round. Your results don't really determine how much study you would do, if that makes sense. Okay, so let's label our axes. Like so. Now, when you rule up your axes, you will need to use a ruler. Okay, I don't have one of those because I am using obviously a digital pen on OneNote here. So, but I want you to, of course, do the right thing. Use a ruler and mark out each increment using your ruler. Okay, so we need to come up with an appropriate scale. So I'm going to look at my first row of data, and I'm going to look for the smallest number and the biggest number. Okay, I think the smallest number there is 0. There is one student who did no study. Okay, and the most amount of study looks like this student here who did 9 hours of study. Okay, so I know that my scale needs to go from 0 to 9. Okay, so use your ruler, maybe mark out 9 centimeters. That would probably be the best option. 0 is going to be here. Like so. Okay, now I'm going to do the same process on the results. Okay, my y variable. So I'm looking at this row here, okay, and I can see the lowest result was 38 by that student who did no study, and the highest result was one student who got 100%. So my y-axis has to go between at least 38 and 100. Now, you could definitely go from 0 to 100 on your y-axis. You could do that. However, it's not always the best option to do that, because if your first value is something like 200 and your highest value is 300, you might want to exaggerate that axis a little bit and skip the numbers between 0 and 200. Okay, so to do that, you just do a little symbol like this. It's a little zigzaggy line. Okay, you could also use that symbol as well, just to show that there is a break in the axes, or that the axis is compressed in some way, just so that's symbolized in some way. So if you would like to start at, say, 30 and go up in tens, you can do so. If you don't want to start at 30, you can start at 0. It's only 2 extra increments. Okay, so do that with your ruler, and then we start plotting the points. So each of these is a dot. So this is person number 1 studied for 5 hours and got 62%. That's going to be 1 dot. The next person studied for 45 minutes, or 0.75 of an hour, and got 48%. Okay, and then the third person studied for 2. You see what I mean? So each one is a discrete dot. Okay, so what I'm going to do is I'm going to find 5 hours on the x variable. I'm going to find 62 on the y variable, and I'm going to put a dot. Now, obviously, the best way to do this accurately would be with grid paper and or a ruler. So I would like you to do it more accurately, whereas I'm just kind of estimating by eye because I'm doing this on OneNote. Okay, so make sure you do this in a more accurate way. There we go. So keep plotting those points out, and you should get your scatter plot. Now, here's one I prepared earlier on Excel. So this is what it should look like. I've also added a least squares line there on Excel, but you don't need to add that at this stage. We're going to learn how to do that later on. Okay, but that's what our scatter plot should look like. Okay, so that's step 1, constructing the scatter plot. Step 2 is to interpret the scatter plot. Now we can describe scatter plots and we can interpret them based on the following features: its form, direction, strength, and outliers. Okay, so form means linear or non-linear, direction means positive or negative, strength can be strong, moderate, weak, or no association, and then outliers can be present or not. Okay, so let's look at some examples. The first one here I have for form, linear or non-linear. You can see these two examples here. The one on the left is a linear relationship, whereas the one on the right you can see is non-linear. It has a curve to it. Okay, so it's important that we are able to identify linear and non-linear because, as I mentioned earlier, one of our assumptions is that we have a linear relationship in our data, because remember, what we are doing is called linear regression analysis. If the data is non-linear, we have to do a different process. You can't do linear regression analysis on data that is not linear. Okay, so that's one of our first assumptions, is that the data is linear. Okay, there have been, if you have a look at the 2020 external exam, you will see that there was a question on there where students had to do linear regression analysis and the data was not linear. It was a bit of a trick question there. Okay, so make sure you always check to see if the data is linear or not. Okay, so that's form. The next is direction, positive or negative. Okay, so positive direction means that the relationship is going up from left to right, whereas negative means the relationship is going down when you read it from left to right. Now, negative does not mean bad, okay? It doesn't mean that there's a bad relationship between the two of them. It means that it's just referring to the direction. Negative means that there is a negative gradient, okay? So if you think back to Unit 1 of Grade 11, where you learned how to calculate gradient, we would know that a negative gradient means that the line is going downwards, okay? So you can see in this example, all this is telling you is that the more someone has to be at university, the less hours they can work, okay? And this makes sense. The more you have to be at university, the less time you have for maybe some part-time work. Someone who doesn't go to university at all can work a lot of hours, okay? So that's what that means. It doesn't mean bad. It just means that there's an inverse relationship. As one thing increases, the other decreases, okay? Our next feature is strength. So we've got 4 possibilities here: strong, moderate, weak, and no association. Okay, and remember, that could mean both positive and negative. So I've given examples of both. And you can see that the closer the dots are together towards making a line, the stronger the relationship is. Okay, and you can see right over here at no association, the dots are just scattered all over the place, so there's no perceivable line. Okay, whereas in weak correlation, you can kind of see that this corner up here is empty, this corner down here is empty, so you can kind of see that there is somewhat of a line happening here, but those dots are very far apart. Okay. In a moderate relationship, they're a bit closer together again. And then in strong, you can see there's a nice tight positive line happening there. Okay, so that's strength. We're going to talk about quantifying that in a minute, putting some numbers to this scale here, but you should also be able to just look at a scatter plot and be able to interpret how strong it is. Okay, and then the last feature is about outliers, whether they're present or not. Okay, so this first example here, there are no outliers. Okay, there's some variability. It's not a strong relationship. It might be more moderate, but there are no outliers. Whereas in this example on the right, there is one outlier. See if you can point it out for me, and then I shall show you. Okay, here's the culprit. This is the outlier. Okay, so if I draw those you can see the straight line that's happening there. Any that are within those two lines are still forming part of the relationship. So sometimes people might think that this one's an outlier. It's just a high value, but it's not an outlier. It's not outside of the relationship that is forming here. Okay, whereas this guy down here is not behaving like the rest of the dots. Okay, it's outside of the relationship. So that's another one of our assumptions with linear regression. The assumption is that there are no outliers. So if you have outliers present, you must identify them, and then you must exclude them from the data set. Because as you'll see as we go along, a lot of our statistics are based on averages, means, okay? And we know that means are very easily influenced by the presence of outliers. You learned that back in Unit 2. Okay, so if our statistics are based on the mean, then those statistics also carry the same limitations. So if the mean is easily influenced by outliers, then also the other statistics will be as well. So if you spot any outliers, you must exclude them from your data set. Okay, so let's have a look at the scatter plot that we drew. And I want you to tell me, describe the relationship of the hours of study versus the result. Pause the video, write it down, and then I'll tell you the answer. Okay, so in terms of form, this one is linear. Excellent. In terms of direction, this one is positive. In terms of strength, this one is strong by the look of it, but we can check some of these things again later. And there are no outliers. Okay, very good. So it is important. So all of these things can be essentially, well, maybe not the last one, but almost all of these things can be verified through our statistical calculations. So you don't even necessarily need to graph your data to be able to come up with these answers. But as you can see, visual inspection can be very important as well, because you need to spot any outliers. They will stand out. And you also need to make sure that it looks like it's forming a straight line. Okay? Now we're on to step 3, which is to calculate the correlation coefficient. The correlation coefficient symbol is a lowercase r. Okay, now this is one of our statistical calculations, and we can use it to measure the strength and the direction of an association. Okay, so it can help us out with both of these two things. Okay, it's calculated with this formula here, and you will see this formula on the formula sheet if you go to the QCAA website, okay, the one that is provided to you in all of your assessment. Now, you're probably looking at that formula and having a little bit of a meltdown because it does look quite complicated, okay? However, there is a way to calculate the correlation coefficient with your calculator, okay? It does the hard work for you. Now, what I will do is I will record a separate video showing you how to do that if you don't know, and I will put it in the title, in the info card and in the description if you want to have a look at that. Okay, so you're probably wondering, well, if I don't have to use this formula, why is it on the formula sheet? Okay, well, I mentioned before that our statistics are often using the mean. So you can see I've highlighted X bar, which means the mean of the X variable, and Y bar, which is the mean of the Y variable. So it's important that you remember that because the mean is being used in this calculation, in this statistic, that you need to use the same assumptions apply. Okay, so if there is an outlier, you must exclude it. Okay, and down here we have standard deviations of x and y. Okay, so that's why that formula is there on the formula sheet, to remind you of those assumptions. Anyway, when you do that calculation, you will get a number that is between 1 and -1, and that depends on if the association has a positive direction or a negative direction. Obviously, if it's a positive number, it means the line is going up, and if it's a negative number, it means the line is going down. So the closer the number is to 1, whether that's positive or negative, the stronger the relationship is. If you get a value of 0, that means that there is no association. Okay, so let's have a look at some examples here. We've got this first one. You can see it's going in a negative direction. Okay, and it looks like it has sort of a moderate strength to it. The dots are fairly far apart. So you can see we have an R value of -0.7. Okay, remember -0.1 would be a perfect straight line going downwards. Okay, but we haven't got that. We do have some variation. Okay, here's our next example. The direction is positive, it's going up, so it is a positive number. But you can see it's even more spread out than the previous example because the number is 0.5. It's a little bit further away from 1 than 0.7. Okay, even more so, 0.3, you can see those dots are really far apart now because we're getting closer and closer to 0. So there's more variation. It's a negative number, you can see the direction is negative. And our last one here, positive 0.9. 0.9 is getting quite close to 1, so as we would expect, we have a much stronger relationship. The dots are much closer together. Okay. Now, how you classify the strength of the relationship as strong, moderate, weak, or no association can be based on the correlation coefficient. So we've got this little table here. Okay, there's lots of different versions of how you might classify this, but this one I like the most because it's kind of in quarters. Okay, so between roughly 0 and 0.25 in both directions, you would say there is no association. So anything below 0.25 is so weak that we would say there's no association. Okay, between 0.25 and 0.5, that's our next quarter, we would call weak. Between 0.5 and 0.75, we would call moderate. And above 7.5, we would call strong. Now remember the highest you could possibly get is a 1. That would be a perfect straight line, okay, which you would only see in something like Unit 3, Topic 3, where we do arithmetic sequences and you get perfect straight lines in an arithmetic sequence, okay? It's very rare in real life to get a perfect relationship, okay? And then, of course, it's the same into the negative. As you approach 1, the relationship is stronger and stronger. Okay, so what I'd like you to do is, if you know how to use the stats function on your calculator, I would like you now to calculate the correlation coefficient of this data. See if you know how to do that. If you don't, I'll put that link up in the info card of me showing you how to do it on my Green Texas calculator TI series, okay? So have a go at that, and then I will tell you what the answer is. Pause the video, have a go. Okay, if you've done that, the answer should be 0.9586. If I'm rounding to 4 decimal places. If you rounded to 2 decimal places, the answer, of course, would be 0.96. Okay, there's not necessarily any guidelines about where to round. It's up to you as long as it's rounded correctly. Of course, if the question specifies where you should round to, follow those instructions. But as long as you've rounded correctly, 2 decimal places and 4 decimal places doesn't really matter that much. Okay, so there's our answer. All right, next step. Step 4 is to fit a least squares line. Okay, now I'm going to explain the name least squares line later on, but I need to teach you something else first before I can explain what that means. Okay, but essentially, a least squares line is used to model the relationship between those 2 numerical variables. Okay, and it uses the equation of a straight line. So this is our least squares line here. Okay, as you can see, it's capturing the general trend of the data, and you can see that there are an equal number of points on either side of the line. Okay, there should be an equal number of points on this side and an equal number of points on this side. Okay, you'll see why that's important later. Okay, so that's our least squares line. Now, we're not going to be fitting that line by eye. You're not just going to be sort of eyeballing it and go, looks like that. Okay, we are actually going to be doing some statistical calculations to create that line, which is where our equation of a straight line comes into play. Now, you might remember that from Unit 1 of Year 11 being y equals mx plus c. Okay, well, we've got slightly different symbols, but it's still the same general formula. Okay, so in this example, we are using the equation y equals a plus bx. Okay, y is still the response variable, x is the explanatory variable, a is going to be our y-intercept instead of c, and b is going to be the slope or gradient of the line instead of m. Okay, so this equation isn't on your formula sheet by itself, so you need to know this one very well. Now, A and B both have formulas for them so that you can calculate them. Okay, but you can also, once again, use your calculator. You need to know both methods. Okay, so here we go. The equation for the slope, there's 2 versions of it. There's this big long one here, okay, or there's a simplified version here. This is the one you actually need to use. Okay, so there might be a question that gives you the R variable, the correlation coefficient, which is R. It might give you the standard deviation of the Y variable. It might give you the standard deviation of the X variable, and you have to substitute all of those values in to get the slope. Okay, and if you remember, the slope estimates the average change in the response variable for each 1 unit increase in the explanatory variable. Okay, now I will give you some examples in a minute of what that means so we can interpret it in a context. But remember, if the gradient is positive, then it's increasing. If your gradient is negative, then your response variable is decreasing in response to the increase in the explanatory variable. Okay, once again, we'll go through an example in a second. So once you've done your calculation over here to find B, you can then substitute that answer into our equation down here. Now, this one might look familiar to you. It looks exactly like the one I showed you before, but rearranged so that you can solve for A. So if you forget your equation, you can always have a look at that one and work backwards. So once you've got your slope, you can substitute that in. The other information you need is the mean of the X variable, the explanatory variable. You also need the mean of the y variable or the response variable. Okay, so once you have all of that information, you can substitute that in and get your y-intercept, which is A. Now, to interpret the y-intercept, you have to remember that the y-intercept is when your explanatory variable is equal to 0, okay? And think about what that means. So if I draw our graph up here or something, this would be your y-intercept when your x variable is at 0, okay? I'll go through an example once again in just a moment. Okay, so here is our data table from before. What I would like you to do is use your green calculator again to input that data. If you don't know how to do that, you can go to the video in the title card again where I show you how to do that and where to read it. Okay, so once you've got that, you can start by writing the equation of the straight line, which is y equals a plus bx, and then substitute those variables into it. So your calculator should tell you that the y-intercept is 39.81, and it should be telling you that the gradient is positive 6.23. You also need to substitute the response variable into the place of the y in this equation, and in the place of x, you would place the explanatory variable, which is in this case the hours of study. Okay, now that you've got that equation of the least squares regression line, I would like you to, as I mentioned in these 2 dot points here, to interpret the slope and the y-intercept of this line in the context of this data. Okay, so pause the video, have a go, and then I will give you an answer. Okay, so let's have a look at that information. We've got a y-intercept of 39.81. Now remember, that is when x equals 0. Okay, so what's our x variable here? Oh yes, it's the hours of study. So that means when a student has done no study, their predicted result is 39.81%, which we all know is a fail because you have to have greater than 40% to pass. Okay, so if you do no study, 0 hours of study, the predicted result is 39.81. Okay, now the slope tells us that for every 1 unit increase in x, y will increase, because it's positive, by 6.23. So what are our units for our x variable? Well, the units are hours. So for each additional hour of study, a person's result should go up by 6.23. Okay, so if you do no study, you're predicted to get a result of 39.81. If you do 1 hour of study, that adds 6.23 to your predicted result, according to this model. So that's what the slope means. So for each increase of 1 unit in the x variable, we have got an increase in the response variable. Increase because it's positive. Of course, if it was a negative value, it would be a decrease. Okay, let's move on to step 5 now and use our equation to make predictions. Okay, so you can use that equation that you came up with to predict the value of the response variable. Now there's two sort of processes that we need to know about here: interpolation and extrapolation. interpolation is where you make a prediction from within the bounds of the original experimental data. So in our case, the experimental data is the dots. So if you look on the scatter plot, the dots go from here to here. So if you make a prediction that is within this range, it is interpolation. Okay? Whereas if you make a prediction outside of the dots, either up here and onwards or down here and potentially onwards, but usually we're only working in the first quadrant of the Cartesian plane, so usually our values are always positive. But down here and up here and beyond is extrapolation outside of the dots, outside of the experimental data. Okay, now it is important that you know that terminology because I saw some questions on the sample and mock and external exams that does get you to actually define those, what process is happening at any given time. So make sure you know that terminology. Okay, now there's a couple of ways that we can interpolate or extrapolate. The first one is to look on our scatter plot. Okay, so if we wanted to predict the results of a person who studied for 6 hours, what we could do is look on our graph, find 6, rule a line upwards, and then rule a line across. It looks like it's something like, I don't know, 78%-ish. Okay, obviously do that with a ruler so you've got that nice and accurate. Okay, so you can do it by reading it off the graph. Okay, now tell me, what did I just do? Interpolation or extrapolation? What do you think? Well, it was in fact interpolation because it was within the bounds of the data. If I was making a prediction about, say, 10 hours here, it would be extrapolation. Okay, but we'll talk about that in a minute. So that's one way to do it. But you can see there are some limitations there. If your scale isn't detailed enough, it's hard to be accurate. Okay, so what you can also do is substitute into the equation of the least squares line. So let's go back to our prediction. We want to predict the result of someone who studied for 6 hours. So we can substitute 6 hours into that part of the equation. Okay, and let's see what we get. Put that into your calculator and you should get 77.19%. Okay, so someone who studied 6 hours has a predicted result of 77.19%. Now, we have to be careful extrapolating too far from the original data, okay, because sometimes the prediction will no longer be reasonable. Okay, so an example here is to predict the result of someone who studied for 12 hours. Okay, so if you substitute that into the equation, you get about, I'll do squibbly, approximately 114%. Now, is it possible to get 114% on an exam? No, it is not. The highest you can get is 100%. So as you can see, we have extrapolated too far beyond the bounds of our data, and now our prediction is not reasonable. Okay, so you have to be careful when you are extrapolating. Okay, now the other reason you might have to be careful is that the model that you're using, the scatter plot and the model that you're using might not stay linear forever. Okay, it might just be at this point in time it follows a linear model, but later on it plateaus or it changes in some way that it becomes non-linear. Okay, so a common example is if you think about a learning curve or a training curve. Let's say you're trying to get better at a sport, or you've just started, I don't know, strength training or something like that, and you will see as you spend more time working on your skill, you will get better at it, okay? And you'll see this excellent linear progress, okay? At some point, however, you will still get better, but you're kind of reaching your potential, so it flattens out, okay? So whilst you can use a linear model between here and here, you cannot use the linear model further on because, as you can see, it's changed, okay? So be careful extrapolating too far away from your original data. Let's say your original data is in here, okay? For an example of this, go take a peek at the external exam from 2020 in the Paper 1 short response section. Question 24 has an excellent version of this, okay? All right, now we are going to do step 6, which is to check the validity of our predictions. We can do that with another statistic called the coefficient of determination, not to be confused with the correlation coefficient, though they are related, as you'll see. Now, the correlation coefficient had a symbol of lowercase r. The coefficient of determination has a symbol of r squared, uppercase. So this is a statistic that shows the degree to which one variable can be predicted from another variable that is related, and it is calculated by squaring the value of r, which is the correlation coefficient. Okay, so it makes sense that the stronger a relationship is, the more you can have a valid prediction from the explanatory variable to the response variable. Okay, you might wonder why we're squaring it. Well, we'll talk about that in a minute, but it's because the correlation coefficient can be negative, and if you square a negative, you should end up with a positive. Okay, we'll do an example in a second, okay? So when you have your r squared value, you can reach a conclusion about it. Okay, and what I've written for you here is a generic kind of fill-in-the-blank version of that conclusion, okay? Because the coefficient of determination can be multiplied by 100 to get a percentage, and that percentage shows that the amount of variation in the response variable that is explained by the variation in the explanatory variable, okay, with the rest being explained by other factors. Okay, so you might want to jot down that generic version, and you can fill in the blanks based on the results you get from your specific example. Let's go back to our example. So here are our hours of study versus results. Okay, I've written down the R statistical calculation again, so our correlation coefficient is 0.9586. I'd like you now to calculate the coefficient of determination by squaring it. Go ahead and do that. Now, this technically isn't part of the syllabus. The syllabus very clearly says that you have to be able to use but not calculate the coefficient of determination, but I'm just going to throw it in here anyway because I think it adds to your understanding of what the coefficient of determination is. Okay, so hopefully you've done that, and if you square this, you should get 0.92, which we can turn into a percentage of 92%. Okay? So what I then want you to do is to decide if a predicted result based on this model would be valid or not, okay, according to our coefficient of determination. Go back to our generic version and fill in the blanks. Okay, here's my answer. We can conclude the following. The coefficient of determination shows us that 92% of the variation in a student's result is explained by the variation in the amount of study. The rest of the variation, which in this case is 8%, the rest of the variation in the student's result will be explained by other factors. Therefore, a prediction based on this model would be valid. 92% is pretty good. Okay, if I said that 92% of your result is explained by the amount of study, that seems like a really good strategy, doesn't it? Okay, whereas if I said 14% of the variation in a student's result is explained by the variation in their amount of study, you would probably think, 14 is not much. I don't like the sound of that. I'm going to try a different strategy. So you would say that that's not valid. Okay? So that's how you interpret the coefficient of determination. Let's do one more example. Here's a different R variable for you, an R value for you of negative 0.5487. Okay, I would like you to calculate the coefficient of determination and draw a conclusion. Would it be valid or not? Pause the video, have a go. Now, my first question for you is, did you get a negative number when you calculated that? Because that's a problem if you did, because a negative times a negative should make a positive value. So that probably happened because you typed this into your calculator. Now what your calculator did was square the number and then just tack on the negative symbol. So if you're going to put this into your calculator, you need to put it with brackets that include the negative symbol. Try it again if you ended up with a negative answer. This time with the brackets. You should get a positive number now. Excellent. So in this case, it was 0.30, which translates to 30%. Now, 30% doesn't seem like a very good model to base a prediction on to me. If only 30% of the variation can be explained, I don't think that's a very valid model if it's something that low. Okay? So that's how you interpret the coefficient of determination. Let's move on to step 7 now, which is to check one of our assumptions. The assumption that we're going to check is that it is a linear model. Okay, we know that's really important. We also know that checking for outliers is very important. And we also know this has to be based on numerical data. Those are sort of your 3 assumptions, that it's numerical data, that it is a linear relationship, and that there are no outliers. You need to check those 3 things. Okay, so we need to construct a residual plot to check if it is a linear relationship. Okay, so when I say residual plot, you're probably wondering, hang on, what's a residual? Okay, well, let me explain. If we go back to step 5, remember we were making predictions. Using our equation of the least squares line. And often what you'll find is the predicted value can be very different from the actual value recorded. Okay, so residuals are what we call the difference between the actual value and the predicted value. And I mean difference literally. We have to subtract. Okay, so you might want to jot down this formula here because it is not on your formula sheet. You have to remember this. Okay, you must recall that a residual value is the actual minus the predicted. Okay, so let's have a look at one of these examples. So if we go back to my example about hours of study versus results, here was our equation. Okay, let's make a prediction about someone who studies 5 hours. Let's use this first one as an example. Okay, so what I want you to do is to predict the percentage result of someone who has studied for 5 hours. Okay? Do that using the equation. So what we're going to do is substitute 5 into that equation, and let's see what we get. I get a value of 70.96%. Okay, now that's our predicted result. Let's have a look at the actual result. So someone actually studied for 5 hours and their result was 62%. So you can see those two things aren't quite the same. Okay, and if you look on our graph, here's that dot point there, and you can see it is not perfectly aligned with our least squares equation, and that's why there's a difference. So let's calculate that residual. Our actual value was 62%, and our predicted was 70.96. Okay? And you might see that that's going to be a negative value. Okay? So our residual value is negative 10.96. Okay? Now, it's not unusual for residuals to be either positive or negative or close to 0, okay? And it has to do with whether they're above or below the line, okay? So if a particular data point is above the line, your residual will be positive because the actual data will be greater than the predicted value. Remember, the predicted value will be on the line. If your dot is below the line, then you will have a negative residual because the actual data is less than the predicted data, which is where the line is. If your dot is exactly on the line, then your residual will be 0. If it's very close to the line, it will be close to 0. Okay? Now remember I said before that that least squares line does tend to run right through the middle of the data, so you should end up with almost an equal number of dots on either side of the line. Okay, that's what you should expect. So what I will do is get you to fill in this table here. Okay, so for each one, I want you to write the predicted result. Let's round to 1 decimal place here. So my previous prediction, let's round that to 1 decimal place, which will round us to 71.0. Okay, and therefore our residual will be negative 11 if we're going to 1 decimal place. Doesn't really matter how many you round it to, just check if the question specifies. But I'm just trying to fit it all in. Okay, so I want you to complete that table. Okay, so come up with the predicted result for someone who studied for 0.75 of an hour, 3/4 of an hour, which is 45 minutes. Okay, write the answer here. You do that by substituting into this equation here. And then, once you've got the predicted result, I want you to calculate the residual value. Remember, it's the actual minus the predicted. Okay, practice that by filling in the table. Pause the video. I'll let you do that, and then I shall show you the answer. Okay, so once you've done that, here's your table. And I've just spotted that I accidentally did that the wrong way. Okay, let's fix that up. My bad. Okay, so that's what that should look like. Okay, if you've done that correctly. And you'll see how many negatives do we have? 1, 2, 3, 4, 5, 6, 7, 8 negative values. 1, 2, 3, 4, 5, 6, 7 positive values. Okay, we've got an odd number of dots here, so it was never going to be even. But you can see there's roughly half positive, half negative. That's very normal. We should have that. Because what we need to do now is turn this into a residual plot. Okay, so we have to graph it like it's a scatter plot, except we want, instead of the response variable on the y-axis, we want the residuals on the y-axis. Okay, so the residual values are going to go on the y-axis. And because we have some negative and some positive, it means our x-axis is actually going to have to be in the middle here. Okay, so if you think about a Cartesian plane, we're using this half of the Cartesian plane. Okay, these two quadrants. So this would be our x-axis here, which is still our hours of study. And then on our y-axis, as I've mentioned, we've got our residual values. Okay, so just like how we did our scatter plot up here, we can use the same scale. Okay. Okay, like so. Obviously, as I mentioned before, when we were doing the scatter plot, please use a ruler. Don't do what I do, which is just guesstimating. Definitely use a ruler or some grid paper. Okay, so now we need our y scale. We can see our biggest drop here is -9. We also have positive 10.4. So let's go, we would have to go at least to 11. So maybe we'll go up in 2s. Like that. Like so. Now we can start plotting. So for 5 hours of study, our residual is -9. So that's going to be down here. For 0.75 hours of study, our residual is 3.5. Like so. 2.5 hours, so halfway between 2 and 3, -1.4. Okay, and you carry on like that. What you should end up with is this. And it looks a bit strange, but this is exactly what it's supposed to look like. We call it random scatter. It should look like the dots have been randomly scattered around this 0 value on the x-axis. Okay, so that's what it should look like. Because to interpret it, a random scatter of points clustered around that 0 line, the 0 x-axis line, would support the assumption that it is a linear model. Okay, so as you can see, I've got a linear scatter plot here. It is negative in direction, and it looks like quite a strong relationship. And this is its residual plot. And as you can see, those dots are randomly scattered, which means that it supports the assumption that it is a linear model. Let me show you one that doesn't. Okay, so here's our scatter plot, and you can probably already see that there's a slight curve happening here, but it can be quite hard to spot sometimes. So doing a residual plot, you can see very clearly that there is a curve there. That is not random scatter. Okay, so we do not have random scatter. The residual plot is showing a clear pattern. There's a curve, and so that indicates that the association is not linear, and you will have to use a non-linear model to analyze this data. We don't study a nonlinear model here in this syllabus, so we would just leave it at that. But it means that your conclusions will not be valid if you use a linear analysis tool on nonlinear data. Okay, so that step, constructing the residual plot, is to check for that assumption. Okay, so going back to the residual plot that we just made, you can see it is displaying random scatter, so therefore it is appropriate to use a linear model to analyze this data. Okay. Now, just a quick note, I promised you I would tell you why it's called the least squares regression line, and I had to do this now because the least squares regression line is the line where the sum of the squares of the residuals are as small as possible. So I had to tell you what a residual was first before I could explain why it's called the least squares regression line. Okay, so the sum of the squares of the residuals need to be as small as possible. So small as possible is the least part, and squares of the residual is obviously least squares part. Okay, now if you want a bit more detail on that, here's an example. You can see here's our line, and we've got roughly dots on either side, and those dotted lines there show you the residuals. So that's the residuals there, the difference between the actual dots and the predicted value. Okay, so what we would do is take those residuals and square them. Okay, why do we square things? Because it gets rid of negatives. Okay, and then what we need to do is make sure that the squares formed, the area of those squares is minimized as small as possible, because then that means the line is a good fit. Okay, so that's why it's called a least squares regression line. That brings us to the end of our 7-step procedure. I can show you how to do all of this on Excel. Check the info card. I've made it as a separate video. So in case you're doing a PSMT on this topic, you can know how to do it on Excel. It's much quicker. Okay, and what we will do now is have a look at some practice questions. Okay, so this first one here is from the publicly available sample external exam. It's on paper 1 and it's part of the multi-choice questions. Okay, so I want you to have a go at this question to the best of your ability, and we will have a look at the answer in just 1 second. Pause the video, have a go. Okay, so this is a reference right back to the very top when we talked about the difference between causal relationships, ones that are caused by the other, and association. Remember, association is not the same as causation. So basically, we want to rule out anything that is concluding that it is a causal relationship, because it is not causal. Okay, so the answer to this question is, of course, C, because it says there could be a causal relationship. Okay, we can rule this one out because it says definitely a causal relationship. We don't know that. Okay, it could be a causal relationship. Okay, and this first one is wrong because it's saying that only positive associations are valid. We know that a negative association is valid too. Okay, for association, not causation. Okay, it just means that there's a different direction to the association. Okay, and this is basically reiterating the same thing. Okay, negative does not mean that there's not a relationship or there's a bad relationship. It's talking about the direction. Okay, all right, this question here is from the QCAA sample IA2, and as you can see, it's question 10. We're going to use this data It's 12 people of different ages ran around an athletics track for 30 minutes. The number of complete laps they ran was recorded and the results are shown below. Okay, now what we're going to do, we're not necessarily, these are the questions that were asked of this data, but I think it would be better if we do the whole seven-step process, okay, on this data and see if you can figure out how to do everything, okay? So with that data, the first thing I would like you to do is construct a scatter plot. Go ahead and do that. Okay, so here's what your scatter plot should look like. Okay, age is the explanatory variable, so that should be on the x-axis, and the number of laps completed is the response variable, so that should be on the y-axis. Okay, so hopefully you were able to do that. Okay, next step, I would like you to interpret this scatter plot in terms of form, direction, and strength, and whether or not there are any outliers. Pause the video, write down your answer. Okay, so this scatter plot shows a strong negative association, and it looks like it might be non-linear, which we can double check in step 7, as I mentioned, because I can sort of perceive a slight curve happening here rather than a straight line. Okay, but like I said, we can check that in more detail in step 7. Step 3, I want you now to calculate the correlation coefficient, which is R. Do that on your calculator. Pause the video, have a go. Okay, you should have got an answer of negative 0.91. Okay, and that should support our conclusion from the previous answer. It is a negative number, so it is a negative association, and 0.91 puts us in the strong classification. Okay? All right, step 4. I want you to now fit a least squares line. And when I say that, I don't want you to draw it on your scatter plot. I want you to enter the data into your calculator and come up with the y-intercept and the slope and write that as the equation of a straight line. Okay, pause the video. Do that now. Okay, so if you've done that correctly, it should look like this. The number of laps is equal to 11.76 minus 0.14 times the age of the participant, okay? You can see in here that the slope is also negative. That's normal because it is a negative relationship, okay? What I would like you to do now is to interpret the y-intercept and the slope in the context of this data. Okay, pause the video, do that now. All right, here's my answer. The y-intercept is 11.76. It's the value when x is 0. In this context, it would mean that a baby, being 0 years old, is predicted to complete at least 11 laps in 30 minutes. This is obviously not reasonable and demonstrates why it's dangerous to extrapolate beyond the bounds of the original data. Okay, and then for slope, I said a slope of negative 0.14 shows the rate at which people's athletics performance deteriorates over time, which makes sense because you would expect as people get older, their fitness might go down, so that kind of makes sense. Not exclusively, but that's the general trend we're looking at here. So we can say a person will be able to run on average 0.41 of a lap less each year that they age. Okay, year being the units of our x variable. Okay, step 5. I want you to now make a prediction. I would like you to predict the number of laps a 60-year-old could run in 30 minutes. Okay, so have a go at that. Pause the video. write your answer. Okay, so to make that prediction, you will need to substitute 60 into your equation. And I got 3.36 laps. But remember, in the context of the data, it was asking how many laps could they complete in 30 minutes. So this does not count as a completed lap. So that's why I rounded to 3 laps of this track. Okay? Now we are up to step 6, check the validity. So I want you to calculate the R² value, and then I want you to draw a conclusion. Pause the video, do that now. Okay, so the R² value should be 0.8281, which would translate to 83%. And here's the conclusion. The coefficient of determination shows that 83% of the variation in the number of laps completed is explained by the variation in age. The rest of the variation, 17%, in the number of laps completed will be explained by other factors. Therefore, a prediction based on this model would be valid. Okay, 83% is pretty good. We're happy with that. And of course, we are up to step 7 now, where I want you to check the linear assumption with a residual plot. Okay, so what you'll need to do is calculate the predicted value for each of the ages and then calculate the residual. Okay, pause the video, have a go at that now. Okay, here is the answer. I've rounded them to 2 decimal places this time. Okay, so that's what your residuals should look like. What I'd like you to do now is to construct a residual plot. Pause the video, do that now. Okay, this is what your residual plot should look like. Okay, hopefully you've got that right. Now, what I would like you to do is interpret this residual plot and come up with a conclusion. Pause the video, do that now. Okay, so I am seeing, as expected, there's a curve. We don't like curves. Okay, so I have said this residual plot shows a curve and not a random scatter of points. So this does not support the linear assumption. The relationship is non-linear, and therefore the linear model that we developed cannot be used. Okay, so that residual plot shows us that we need to use a different model, a non-linear model. Okay. So there's just one other question I'd like to throw in that I forgot to put in my little presentation here, which I'll quickly do now. So let me give you some data, and I would like you to come up with the equation of the straight line of this data. Okay, so here we go. Our mean of x is 2.4. Our mean of y is 26,093. Our standard deviation of x, my bad, is 1.69. And our standard deviation of y is 19,216. And the correlation coefficient is negative 0.91. So that's the information I'm giving you. I would like you to come up with the equation of the straight line, the equation of the least squares line according to this data. Okay, pause the video, have a go. Okay, if you're really stuck, go back and check the formulas for the slope and the y-intercept. There's your hint. Okay, so to calculate the slope, we need this formula here. Okay, so we're going to substitute the r value in there, and then those values there. Okay, and if you pop all that into your calculator, you should get negative 10,347.08 as our slope. Okay, for the y-intercept, the formula is a equals the mean of y, take away the slope, and the mean of x times the mean of x. Substitute those values in. So our mean of y is that, and then our slope, which we calculated from down here, is that. And our mean of x is 2.4. Put all that in your calculator, and you should get a y-intercept of this. Okay, so our equation of the line, remember it's y equals a plus bx, should be that's an 8. Let me try that again. There's our equation of that line. Okay, so that's pretty much covered all of that topic now. Okay, put any questions that you have in the comments below, and good luck with your studies.